Okay, here's a thought. What if the very foundations of modern computing, the digital world we live in every single day, weren't forged in some high-tech Silicon Valley lab?
Right, or like a secret British bunker like Bletchley Park.
Exactly. What if instead it all started in a German living room during World War II, no less,
Uh-huh.
and all by a single, really determined civil engineer?
It sounds almost unbelievable, doesn't it? But that's the story of Konrad Zuse.
It really is, and that's the mind-bending question we're peeling back the layers on today. We're uncovering this remarkable and honestly often overlooked story of Konrad Zuse.
A true unsung pioneer. His ingenuity really did profoundly shape the digital landscape we all inhabit now.
Totally. So our mission in this deep dive is to explore his groundbreaking inventions. We're talking hardware and software often developed in, well, surprising isolation.
Yeah, we want to reveal why so many people consider him the true father of the modern computer.
And understand the impact, the enduring impact of his visionary ideas.
And to do that, we've looked at a mix of historical accounts, technical details, sources like the Computer History Museum, Wikipedia, and a really insightful book, Computing's Unsung Pioneer.
Right, trying to get a full picture. So, okay, let's embark on this incredible journey.
Let's do it.
So, Konrad Zuse, born in Berlin, 1910, eventually gets a degree in civil engineering in 1935.
Pretty conventional start, you might say.
Yeah, nothing too out there. But then he gets his first job after graduating at the Henschel Aircraft Company.
Okay.
And that's where it hits him. He found the sheer volume of routine manual calculations just mind-numbing, repetitive, awful.
Well, I can imagine. For engineering problems, especially aerodynamics back then, endless calculations.
Exactly. He's looking at these stacks of paper, all this arithmetic, and just thinking, there has to be a better way.
That frustration, that's the spark, isn't it? The need to automate.
That was absolutely the spark. And so in this amazing display of independent spirit, Zuse decides, okay, I'm going to build that better way myself.
Does like that.
Pretty much. He starts building his first machine, the Z1, right there in his parents' apartment in Berlin.
In their living room.
Seriously.
Yep, between 1936 and 1938. Picture it. The living room turns into this workshop.
Wow. Okay, so what was the Z1 like?
Well, it was a floating point binary mechanical calculator, limited programmability.
Okay, floating point binary, that's important. So it could handle decimals, complex numbers for engineering.
Crucial for that, yeah.
Mm.
Not just whole numbers. And get this, the instructions. Punched onto used 35 millimeter movie film.
No way. Movie film.
Talk about resourcefulness. But it was complex. Something like 30,000 intricately cut metal parts, all assembled by hand.
30,000 parts, mechanically.
Yeah. And because of the limits of mechanical precision back then, it never really worked reliably.
That's tough.
All that work.
And then the real tragedy, wartime. The Z1, along with all its original blueprints, completely destroyed in a British air raid. January 1944.
Oh, gone. Just like that. What a loss.
A huge loss.
Indeed. And, that isolation you mentioned earlier, being cut off from resources, from what others might have been doing elsewhere, it really shaped his approach, didn't it?
Seems like it.
He was working completely outside those, Anglo-American academic circles who were also thinking about computation. But he arrived at remarkably similar solutions, sometimes even ahead of their time.
So it wasn't just genius can pop up anywhere.
Well, it's that, but also his isolation, while it definitely delayed his recognition, it might have been a kind of double-edged sword.
How so?
It freed him, maybe, from the way things were supposed to be done,
Yeah.
from the established thinking. It let him dream up things like Plankalkül, which we'll get to,
Yeah.
without, peer pressure staring him down more conventional roads.
That's a really interesting point. Isolation as both a handicap and maybe a catalyst for something truly original. But do you think that solitary path ultimately cost him, broader, earlier influence?
That's the million-dollar question, isn't it? It absolutely delayed his global recognition. No doubt. If he'd been part of a bigger network, maybe his work gets adopted, built on much faster, could have sped up the whole field.
Right.
But then again, would those collaborations have maybe watered down his really radical ideas? It's a fascinating paradox. The very thing that allowed this breakthrough thinking also kind of trapped it, at least for a while.
An astonishing level of independent discovery, either way.
Yeah.
Okay, so World War II intensifies. Zuse's work takes a surprising turn.
Yeah, he gets called up for military service in 1939. But then, crucially, someone realized his work might be useful.
So he was given resources to keep going.
Exactly, which led first to the Z2. That was basically revised Z1, but smartly switching from those tricky mechanical bits to using telephone relays.
Yeah.
Much more reliable.
Telephone relays, like old switchboard parts.
Pretty much, yeah, electromechanical switches. And then in 1941 came the real game changer.
The Z3.
Z3. This is the big one. This is the one. Built in his workshop. Widely seen now as the world's first fully operational program-controlled electromechanical digital computer.
Okay, break that down. Program-controlled, electromechanical.
Digital.
Right. So program-controlled means it could follow stored instructions. Electromechanical means it used those relays, not purely mechanical parts. And digital, using binary, those ones and zeros. It was a binary 22-bit floating point calculator. Again, using those telephone relays, apparently largely scavenged from discarded stock.
Still resourceful.
Always. And it was programmable with loops, which is a key feature, though it couldn't do conditional jumps like if this, then do that. He actually demonstrated it publicly, May 12, 1941.
And the military was interested this time.
Yes. The German Aircraft Bureau actually bought one. They needed it to solve complex aerodynamic problems for aircraft design. That funding helped finance its development.
Okay, and here's a detail that just blows my mind. Zuse was completely unaware of Alan Turing's theoretical work on computation, right?
Completely separate paths at this point. Yet, the Z3 was later proven to be Turing-complete.
Which is incredible. And Turing-complete is, the benchmark we still use today. It basically means a machine is theoretically capable of solving any problem that any modern computer can solve, given enough time and memory.
So this machine, built with relays in wartime Berlin,
was fundamentally as powerful in theory as the supercomputer in your pocket today. He achieved that benchmark independently with scavenged parts. It's monumental for that era, truly.
It really puts his achievement into perspective. He reached this incredible level of sophistication basically alone.
Mm-hmm.
But despite how revolutionary it was, despite its practical military use, when they asked for funding for an electronic version, using vacuum tubes, as his colleague Helmut Schreier suggested.
Denied. The request was denied as strategically unimportant.
Strategically unimportant. Wow. Looking back, that decision feels like it just slammed the brakes on German computing development. A massive missed opportunity, wasn't it?
Absolutely. A huge what-if in history. It's a stark reminder, really, of how politics, military priorities, or maybe just a lack of vision can completely change the course of technology.
Yeah.
Think about it. They had a working, programmable computer. They had a path to a much faster electronic one. And it gets dismissed. This wasn't just like a technical oversight. It profoundly shaped who would lead the computing revolution after the war.
It makes you wonder, doesn't it, about funding decisions today? Are we still sometimes too focused on the immediate applied stuff and missing the foundational, maybe revolutionary research?
That's the chilling question, isn't it? Are similar judgments being made right now, maybe about AI or quantum computing, that we'll look back on as equally short-sighted, these sort of Faustian bargains, maybe?
A powerful and maybe worrying parallel. And Zuse wasn't just doing general-purpose computers either, right? He built specialized machines, too.
Precisely. During that same period, 1941 to 1945, he developed the S1 and S2 machines for the Aerodynamic Research Institute.
S1 and S2, what were they for?
These were special-purpose devices designed specifically to compute aerodynamic corrections for radio-controlled glide bombs.
So, precursors to cruise missiles.
Essentially, yes. And the S2 was particularly advanced. It was the first process control computer.
Process control? What does that mean in this context?
It means the computer could directly monitor and adjust a physical process in real time. The S2 had an integrated analog-to-digital converter.
Okay.
So it could take in continuous analog data from the bomb's sensors, like air pressure, maybe angle convert that into digital signals the computer could understand, process it according to its program, and then send commands back out to adjust the bomb's flight.
Wow. So it's computing integrated directly into a dynamic real-world system.
Exactly. It's an early glimpse of automation, of cybernetics. It shows Zuse wasn't just thinking about calculation, but about application, how these machines could interact with and control the physical world, even under really demanding conditions.
Incredible foresight again. So he's a hardware genius, clearly. But he's also thinking deeply about how to use these machines.
That's the next leap. While he's building the Z4, his next big machine, he realizes something fundamental.
What's that?
Programming in raw machine code, just feeding the computer strings of ones and zeros, it's incredibly tedious, error-prone, cumbersome.
Yeah, I can imagine.
He saw there had to be a better way, a higher level of abstraction, a language closer to human logic, to mathematical formulas, to tell a computer what to do.
And this leads him to...
Plankalkül, developed between 1943 and 1945. Plankalkül literally means plan calculus.
And this wasn't just any programming language.
This was arguably the world's first high-level programming language, designed years before Fortran or COBOL.
What made it high level? What could it do?
It was packed with concepts that were way ahead of its time, things we take for granted now. Arrays, records for organizing data, loops, conditional statements, structured programming ideas.
Stuff that's fundamental to coding today.
Absolutely. And to show its power, he even designed, conceptually, the first real computer chess engine using Plankalkül. He laid out how a machine could analyze the board, strategize moves, using his language.
The chess engine. In the mid-40s.
The plan for one, yes, using his language. But, like much of his work, Plankalkül's impact was delayed.
Isolation again.
Mostly. It was designed by 1945. It was part of his PhD thesis work, but it stayed largely unpublished until 1972.
72. Decades later.
And it wasn't actually implemented, like run on a computer, until 1975.
Wow. So did it influence anything in the meantime?
Subtly, yes. Heinz Rüdeshauser, who was one of the key figures behind LG58, a very important early language that influenced many others.
Okay.
Rüdeshauser actually acknowledged Zuse's Plankalkül as an early attempt at this kind of algorithmic language. So the ideas did eventually sort of percolate into the mainstream, but much later.
And the PhD thesis itself, the one detailing Plankalkül, there's a story there too, isn't there?
Oh, yes. The ultimate irony, perhaps. His monumental thesis, laying out the world's first high-level language, was rejected.
Rejected? Why? Was the work flawed?
Not at all. It was rejected because Zuse, probably completely absorbed in his revolutionary work, forgot to pay the 400 Deutschmark university enrollment fee.
You cannot be serious. He forgot to pay the fee.
That's the story. And administrative oversight nearly buried this incredible intellectual achievement.
That is, wow. Almost a perfect, painful metaphor for his whole career, isn't it?
It kind of is. Brilliance meets bureaucracy. Groundbreaking ideas facing these, mundane obstacles. It just highlights how far ahead he was. Maybe even the academic system couldn't quite process what he'd done.
Yeah.
And connecting this to the bigger picture, Zuse's foresight with Plankalkül was just immense. He saw the need to separate hardware concerns from software concerns. He understood we needed to move away from programming in raw bits and bytes. Decades before that became standard practice.
A true visionary, seeing a future for computing others hadn't even glimpsed yet.
It really makes you wonder how many other breakthroughs might be out there, waiting for their moment, maybe overlooked for similar reasons.
That story, that insight, it really emphasizes Zuse's resilience, doesn't it? And the often messy path innovation takes.
Absolutely. Because after the Z1, Z2, and Z3 were destroyed in the Berlin bombings, he didn't quit.
Kept going with the Z4.
Yes, he managed to move the partially finished Z4 out of Berlin, February 1945, hauled it by truck through war-torn Germany to Göttingen, an incredible feat in itself.
Just getting it out must have been harrowing.
Imagine. Then after the war, he gets back to work on it, and it's finally finished and delivered to ETH Zurich, the Swiss Federal Institute of Technology, in July 1950.
And the Z4 was a big deal.
Huge deal. For a time, it was the only working digital computer in Central Europe.
Wow.
And it holds the distinction of being the first computer in the world to be commercially sold or loaned. It beat the American BINAC, technically, because the BINAC never really worked properly after it was delivered.
So the first commercial computer success story, really.
You could say that. And it directly inspired the Swiss to build their own first computer, the Ermeth.
And Zuse didn't just build machines, he built a company too, right?
He did. Ever the entrepreneur. He had actually founded Zuse Apparatebau back in 1941. After the war, it became Zuse KG in 1949, one of the very first computer companies anywhere.
What kind of machines did Zuse KG produce?
Various models. The Z11 was popular with the optics industry and universities. Then there was the Z22, notable for being the first computer with magnetic core storage memory.
Magnetic storage, okay. Another step forward.
Definitely. Eventually, Zuse KG was absorbed by the German giant Siemens, but that actually helped spread his designs and his innovative approaches through the European computing industry.
So his influence did eventually spread commercially.
It did, but this brings us back to that key point.
Yeah.
The cost of his wartime isolation. His groundbreaking work just wasn't widely known outside Germany for years. Because of the war, because communication was cut off, it meant many of his brilliant ideas, binary arithmetic, floating point, program control, even Plankalkül, were independently rediscovered elsewhere, years later, sometimes decades.
So others got the credit, or at least the initial recognition?
Often, yes. IBM did take an option on his patents in 1946, which is interesting. But that broad international impact, that direct influence he might have had, significantly delayed.
It's a powerful reminder, isn't it, that the best ideas don't always win out immediately. Sometimes it's about timing, communication.
Or just not being cut off by a world war. It shows how history isn't always neat.
Absolutely. Now, beyond the engineering, Zuse was also, well, a deep thinker, almost a philosopher of computation in his later years.
He really was. He continued to explore these big ideas. In 1969, he published a book called Rechnung der Raum.
Calculating space.
Right. And in it, he put forward this pretty radical idea for the time.
Which was?
He suggested that the universe itself, the entire cosmos, might fundamentally be a kind of computer, running on something like a cellular automaton.
Whoa. Explain cellular automaton.
Think of it like a vast grid, maybe invisible. Each tiny point or cell in the grid follows very simple rules based on its neighbors. And from those simple local rules, interacting over and over, all the complexity we see in the universe, physics, chemistry, maybe even life could emerge.
So the universe as digital information being processed.
That's the core idea. It's now known as digital physics, and it's still a topic physicists and cosmologists debate today. Was Zuse onto something fundamental back in '69?
That is genuinely mind-bending, and he kept building things, too, even late in life.
Oh yeah, he conceptualized and created this purely mechanical modular tower, the helix term, between 1989 and 1995. It was designed to be able to assemble and deconstruct itself purely mechanically.
A self-assembling tower. Wow.
And maybe most poignantly, between 1987 and '89, he undertook this massive project, recreating the Z1, his first machine.
The one destroyed in the bombing. He rebuilt it.
Meticulously recreated it. It was a huge effort. Cost something like $500,000, mostly funded by Siemens and enthusiasts. He even suffered a heart attack during the project.
Oh my goodness. That's dedication.
It speaks volumes, doesn't it, about his need to see that original vision realized, preserved.
What about his personal life, briefly?
Well, he married Gisela Brandes in 1945. They had 5 children. Importantly, he was never a member of the Nazi Party.
But he did work for the war effort, building those S1 and S2 machines.
He did. And he reflected on this later. He suggested scientists often find themselves making a kind of Faustian bargain with questionable interests.
A Faustian bargain. Sacrificing principles for resources or the chance to work.
That seems to be the implication. Given his context, working on military projects for that regime, it's a really profound and probably deeply personal statement. It touches on that ethical tightrope scientists can face. Do you take the funding, the resources, from sources you might disagree with in order to pursue the science?
A dilemma that hasn't gone away, has it?
Not at all. It's relevant today with funding for AI research, biotech, military tech. Where does the money come from, and what are the strings attached? Zuse's reflection is incredibly insightful.
A timeless observation. And on a lighter note, apparently he was an atheist, enjoyed painting, signed his work with a pseudonym.
Yeah, Konrad Zuse, a bit of an artistic alter ego. And he left us with a quote that feels incredibly relevant today.
Which one is that?
The danger of computers becoming like humans is not as great as the danger of humans becoming like computers.
Oof, that hits home, doesn't it? Especially now.
Definitely makes you think. He received numerous awards later in life. Recognition finally came. The Werner von Siemens Ring in '64, the Computer History Museum Fellow Award in '99.
So pulling it all together, what does this story mean for us today?
Well, Zuse's story is this powerful reminder that innovation can truly spring from anywhere, often against incredible odds, and that genius isn't always recognized when it first appears.
And it forces us to think about those ethical dimensions, too.
For sure. The choices scientists make, the context they work in.
So, to recap then, Konrad Zuse, his contributions were just immense, profound, and yet for so long pretty much overlooked by the wider world.
He built the first programmable digital computer, the Z3.
He invented the first high-level programming language, Plankalkül.
Laid the conceptual groundwork for so much hardware and software development.
That visionary loneliness we talked about, it meant his ideas were decades ahead. They eventually resurfaced, reemerged, became central pillars of computer science.
Influencing the very way we design technology, how we interact with it.
Which leaves us with a really important question, a provocative thought for you, the listener, to maybe mull over.
What is it?
If Konrad Zuse's work hadn't been so isolated by the war, if Plankalkül, his high-level language, had actually been widely adopted much earlier, back in the late 40s or 50s,
How different would things be?
Exactly. How might the entire trajectory of computing history have changed? Would we have gotten to where we are now even faster? Or maybe in a fundamentally different way, perhaps a more intuitive way, based on his logic.
That's a fascinating what if.
It is. And as you think about that, maybe also consider the other unsung heroes out there whose independent efforts might parallel or even precede the innovations we usually celebrate. It's a reminder that history, especially tech history, is often way richer and more complex than the standard stories we tell.